This is Lecture 2 of Module 6 from the book Problem Solving Guide for Mechanics and Thermodynamics. The subject is two-dimensional collisions. Previously we covered one-dimensional collisions in a line. Here we cover collisions in a plane. So we will be using both the x and the y directions. The transition from one-dimensional collisions to two-dimensional collisions is similar to the transition we made in Modules 1 and 2 when we went from one-dimensional kinematics to two-dimensional kinematics, that is, motion in a line to motion in a plane, or projectile motion. If you're fluent at getting the components of a vector and getting a vector from its components, you should have no problem. It should be an easy transition. The biggest hurdle is understanding the concept of conservation of momentum. That's the big hurdle. If you can do conservation of momentum in one direction, you should be able to do it in two directions. A two-dimensional momentum problem is just two one-dimensional momentum problems. The conservation of momentum equation, the vector equation, is P initial vector equals P final vector. But we split that into two non-vector equations. We conserve momentum in the x direction, P initial x equals P final x, and we conserve momentum in the y direction. P initial y is P final y. That's it. There are no new equations. We just do conservation of momentum one direction at a time. So let's do a problem. We have a carnival game. We shoot 1 gram BBs at a puck. The puck is 50 grams. Try to get the puck into a goal. There's another guy over here shooting BBs. He's got a machine gun shooting BBs. We're just going to shoot one BB. Starts off at 25 meters per second at 25 degrees from the vertical, like this. Ricochets off the puck, bounces this way with 15 meters per second at 30 degrees from the horizontal axis. What's the puck doing after the collision? That's the question. The initial momentum in this system is only that of the BB. The puck's at rest. So with the axis shown, the x-axis horizontal, the y-axis vertical, this initial momentum has a component that's horizontal, right here, and one that's vertical, right here. And we can calculate them. The initial momentum in the x direction, the mass is 1 gram, 25 meters per second sine 25. This is opposite the 25-degree angle. This part right here, we get 10.57 grams meters per second. In the y direction, we use cosine, that's the adjacent side, and we get 22.66 gram meters per second. That's the initial momentum in the system. It's the only thing that's moving initially. If we know what the BB is doing finally, we know that the initial momentum is equal to the final momentum, we can figure out what the puck's doing. So let's get the final momentum of the BB in each direction. We have 15 meters per second at 30 degrees. The y component is 1 gram, 15 meters per second sine 30, which is 7.5 grams meters per second up. In the x direction, it's also positive. 1 gram, 15 meters per second cosine 30, the adjacent side, and we get 12.99 grams meters per second. We can certainly write the equations, and we can do the math, and we can solve for the momentum of the puck. But a picture is so much better. A picture is worth 1,000 words. So let's see what's going on so we can really understand what's going on. So the initial momentum is this. There's the y, there's the x. We just calculated these. It's going in this direction, 25 degrees. You can imagine a vector right here. That's the initial momentum in the system. The puck's not moving. Now let's calculate the final momentum of the BB. We know it's going 15 meters per second at 30 degrees. We calculated its two components. The y component is 7.5, and the x component is 12.99. What's the puck doing? Well, the initial momentum has to be equal to the final momentum. Here we have 22.66 gram meters per second up, and here we only have 7.5 gram meters per second up. The puck must have the rest. In order to conserve momentum in the y direction, the y component of the momentum of the puck must be 22.66 minus 7.5, which is 15.16 gram meters per second. And there it is. 15.16 plus 7.5, that's 22.66. Momentum in the y direction is conserved. Now let's consider the x direction. The initial momentum is 10.57, And now we have 12.99. It got more. How did it get more? Momentum's conserved. Well, the puck's got to be going to the left. 12.99 minus 10.57 is 2.42 to the left. It's got to be right here. There it is. So momentum in the x direction is conserved, momentum in the y direction is conserved. That is the principle of conservation of momentum. What about the speed of the puck? It asks us for the speed of the puck. Let's not forget what the problem asked for. We have the final momentum components. We can get the magnitude, p sub x squared plus p sub y squared. There's the x, there's the y. And we get the final momentum of the puck. That's the magnitude. We can get the speed. We just divide by the mass. That is mv, divide by the mass, and we get 0.31 meters per second, not very fast, as expected, because it's 50 times heavier than the BB. Now we can get the direction. We can use tangent. We can get either angle. I'm saying on the opposite side is 2.42, that's over here, so we're going to get the small angle, the angle with the vertical. Take the arctangent of both sides, and we get 9.1 degrees. So it's 9.1 degrees to the left of the vertical axis. So this velocity of the puck is 0.31 meters per second, 9.1 degrees to the left of the vertical axis. That's the answer to the question. Another nice way to demonstrate conservation of momentum is to use the actual vectors with a 2-scale diagram. So let's do it. Well, I'm going to do it. You watch. You should be able to do it yourself to confirm that momentum is conserved. Here we're working with the components. Let's work with the actual vectors. The initial momentum vector is 1 grams times 25 meters per second. That's the magnitude, and it's like that. That length is 25 gram meters per second. There's the initial momentum. Now we have to put the final momentum on here and hope it's the same vector. The final momentum has 2 pieces. That's the BB before the collision. The final momentum of the BB is 15 grams meters per second at 30 degrees. There it is. The puck is 15.35 grams meters per second, 9.1 degrees to the left of the positive y-axis. And there it is. There's the puck after the collision. There's the BB after the collision. If you add these 2 vectors, you get that vector, which is the initial momentum vector. The initial momentum vector is here. The final momentum vector is exactly the same. Momentum is conserved. P initial vector equals P final vector. We didn't use energy at all in this problem. We can write conservation of energy, but there's going to be some thermal energy generated during the collision. So we can add another equation, but we add another unknown as well, and that doesn't help. Adding another equation with another unknown doesn't help unless they ask specifically for the thermal energy generated. We could do that. So there's numerous problems in the textbook that ask for thermal energy generated. You should be able to know how to do that. Here's a couple final notes about this module. To test your fundamental understanding of the conservation of momentum and the conservation of energy, do problem 8 on problem 203 in the text. No peeking at the answers until you invested a lot of time thinking about them. Momentum problems always involve more than one mass. There are multiple ways masses can interact. They don't have to actually collide. 2 planets can interact with each other. An asteroid can interact with a planet. Momentum is conserved. Electrical charges can interact without colliding. They can put forces on each other. Momentum is conserved. For a good example of this, see problem 6.31 in the textbook. Here we have a car that goes up a ramp, and this ramp is on a frictionless surface. So when this car starts to go up the ramp, this surface starts to move. It's a hard problem. Your goal when you do problems is to understand the concepts. This is physics. You have to think. This is about thinking, not plugging numbers into equations. That's lecture 2.